And we are back. All right, today we are going to talk about the factors that influence stability and structures of ionic compounds. And remember, ionic compounds, it's the attraction between a positively charged cation and a negatively charged anion. So that's one part that affects it. So how strongly the ions attract each other, part of that is dependent on the charge of both the anion and the cation. And the other factor, how close those two ions are to each other, is the size. And those two factors, we say, indicate the lattice energy. So that's the energy of how two ions, the cation and the anion, are attracted to each other in the solid state. In ionic compounds, we always consider them in the solid state. Okay, so lattice energy is defined as the change in energy that takes place when gaseous ions are packed together to form an ionic solid. So, for example, we have a metal cation in its gaseous state reacting with a negatively charged nonmetal anion. We'll call that X minus as a gas, and we form, as long as those charges are the same, Mgx, and that is in its solid state. Okay, so the two factors that affect lattice energy. So this K is a proportionality constant, so we can ignore that. Q1 and Q2 are the charges on the ions. So that means that lattice energy is directly proportional to the charges on the ions, and then it's over R, which you can think of as radius, or the distance between the cation and the anion. So the sizes of the two ionic compounds, the two ions in that ionic compound. So some sources of comparison here. So let's say we want to figure out what's the difference, what has a larger lattice energy, lithium fluoride or beryllium oxide. So if we look at it here, lithium is right next to beryllium on the periodic table, and fluorine is right next to oxygen on the periodic table. So even though they have slightly different atomic radii, lithium is slightly bigger than beryllium, oxygen is slightly bigger than fluorine, so their sizes, the R, is about the same. But if we look at the charges, LiF, lithium fluoride, is made up of lithium plus 1, fluorine minus 1. Beryllium oxide is made up of beryllium 2 plus and oxygen 2 minus. So that means the one with the largest energy, lattice energy, is going to be the one with the greater charges. And especially since it's plus 2 and minus 2, if we look at that ratio, Q1 times Q2 plus 1 times negative 1 will be negative 1, whereas this will be negative 4. So that means the lattice energy for BeO will be 4 times as high as LiF. So same thing here, beryllium oxide would have a greater lattice energy than BeF2, because if we looked, it would be Be2 plus and F minus. So around the same sizes, but now plus 2 times negative 1 would be negative 2. So those are the ratios looking at the relative charges there. And always lattice energy will be negative. It will be what we call exothermic. Energy is released because you have those two oppositely charged ions, the positively charged cation, negatively charged anion, are attracted to each other, and when they're attracted and form that bond, they release energy, and those charges will always be opposite. And so that's in terms of different charges. We can also think about it in terms of size. So if we look at lithium fluoride versus NaCl, all of those have the same charge, +1, -1. However, if we look at lithium and fluorine are both in row or period 2, lithium only has 1 energy level, fluorine has 2, but if you look at Na+, Cl-, those are respectively below lithium and fluorine on the periodic table. So sodium has 2 energy levels, 1 more than lithium. Chlorine has 3, 1 more than fluorine. So that means since NaCl is bigger, since it has a larger radius, that means lithium fluoride will have a larger ionization energy. And same thing if we went another energy level down, like let's say we had KBr, that would have the lowest ionization energy of the 3 because it still has charges of +1, -1, but it would be even bigger than NaCl, so it would have the smallest lattice energy of the 3. So with ionic compounds, we're just thinking about, okay, a discrete positive charge, negative charge, and then in the middle here, we have polar covalent compounds, where there is a dipole moment, where there's a side with more a partial negative charge, and a side with a partial positive charge. And the partial negative charge always goes with the atom that has the higher electronegativity, and then we have pure covalent compounds in which that electronegativity is the same, and those are normally diatomic molecules. But even though we go from pure to polar to ionic, no bond reaches 100% ionic character. So no bond reaches 100% ionic character, even if there's a large electronegativity difference. Just know that ionic character is directly proportional, increases with the electronegativity difference. So you don't have to know this equation at all, just know that ionic character, as the difference in dipole moment increases, as that electronegativity difference increases, as does ionic character. So there's no totally ionic bonds between atoms. They have large percentages of an ionic character, but never 100%, as you can see from this chart. So if you remember from the lab, even covalent bonds have some ionic character. It's just a low percentage. Like if you look at all these covalent bonds, just their ionic character is all below 25%. And normally, for the most part, any ionic bonds have greater than 50% ionic character. So most covalent bonds have below 8% ionic character, below 25%. Most ionic bonds have an ionic character generally greater than 50%. And as you will see in class, any compound that conducts an electric current, remember when we talked about Gatorade, those were electrolytes, when melted, will be classified as ionic. So something like salt breaks apart into its constituent ions, Na+, Cl-, whereas covalent compounds, and as you'll see with sugar or any other covalent compound made up of nonmetals, even though sugar dissolves in water, it does not break apart. It does not, what we say, dissociate into its ions. All right, that's it for today. See you next time.